In May of 2022, I created a video about how to make a day-night cycle in Unity which syncs with real-world time. There were some flaws and some issues that were pointed out in the comments section, which I started to address in a new video. That video never saw the light of day until recently when I stumbled across it. I figured it would still be worth posting even though it's a little bit later now, so here it is. I hope you'll enjoy it. About a week ago, I received this comment on the video. It said, "Hi, I want it so that it will rotate the whole time around, but right now the rotation stops when it reaches sunset and starts at sunrise with a jump. Can it just rotate the whole night?" To that I actually say yes. Yes, it can. In fact, it should have already been doing that the whole time. Why on earth would I code something that doesn't do that in the first place? So, naturally, I cracked open my code to see this. It says if the time into the day is less than the sunrise time, or if the time into the day is greater than the sunset time, in other words, if it's nighttime, snap the sun's rotation to 185 degrees. Well, there's my problem right there. So, why did I code it like this? Let me explain it like this. So, for simplicity's sake, let's do everything in 24-hour time. Our day is 24 hours long, and let's say we want our sun to rotate a total of 360 degrees around the Earth. That means from sunrise to sunset, the sun needs to move from 0 to 180 degrees. So let's say in this example that we want our sun to rise at 8 a.m. and set at 8 p.m., or 20 hours. Then we would want our sun to move from 0 to 180 degrees across that amount of time. So first we should calculate what the position of the sun should be based on the real time, which actually we just need to find the missing numerator. In this case, it's pretty easy. We can do so just using the following algorithm. Our current time into our solar day over our solar day length is equal to the current percentage of sun movement over the degrees of total sun movement desired. So in other words, we can use cross multiply and divide. Thanks to my grade 7 math teacher, that's super easy. We just do time into our solar day times our total desired degrees of movement divided by our solar day total length will give us our percentage of sun movement where we want our sun to be located. And as long as the current time is within our solar day window, then it's easy to calculate some of these missing variables. And we can calculate how long our sun should be visible in the sky by taking the sunset time and subtracting the sunrise time. Then we would be able to see that the sun was in the sky in this example for 12 hours of the day. Or in other words, we would have a solar day length of 12 hours. Finding our time into our solar day can be done simply by taking the current time and subtracting the sunrise time. So let's say in this example, the current time is 3 o'clock in the afternoon, or 1500 hours. What we would do is we would take 15 and subtract 8, the sunrise time, which would give us 7 hours currently into our solar day. So you can just fill in the blanks. 7 over 12 is equal to blank over 180 degrees of movement, assuming that we want our sun to move from 0 to 180 degrees, of course. So, in other words, 7 times 180 divided by 12 is equal to 105 degrees, which, if we put the sun to 105 degrees, that looks right about exactly where we want it for 3 o'clock in the afternoon. What happens if our day is longer than 12 hours? Now, this is something I can confidently say I had never considered before, but did you know that at the center of the Earth, along the equator, the length of a solar day is always exactly 12 hours? And it's because of the 23.5 degree tilt of the Earth that other parts of the world have longer days and shorter nights, or vice versa, depending on what time of year it is. So technically our algorithm works totally fine if everyone that we wanted to play our game lived exactly along the Earth's equator, but sadly, however, I have a feeling that that's not the case. And I have a feeling that the majority of the people who are going to be playing our games won't necessarily live exactly along the equator, so how do we compensate for the changing lengths of days and nights? Well, in a sphere planet, it's actually not that hard at all. Because of the tilt and the rotation of the Earth around said tilt, days will automatically become longer and shorter depending on where you live in the Earth. And you can imagine if the tilt were the other way, instead of having long days, we would have long nights, or of course vice versa. However, although the tilt of the Earth itself never actually changes, the Earth rotates once fully per day, but it also goes around the sun once fully per year. So if the planet was all of a sudden on the other side of the sun, or our light source was coming from the other direction, you can now see that where there were before longer days will now have longer nights, and vice versa for other parts of the planet. So why don't we just take the algorithm we used for the day and flip it and use it for the night? If the solar day was 17 hours long, then our solar night should be 24 hours minus 17 hours equals 7 hours long. Now we just have to find how long we are into our solar night based on the real time. Well, that's not too hard. We can split it up into two different sections, before sunrise and after sunset. Because remember, if we have a 24-hour day, the day always resets at midnight. So if it was post-sunset, or if the current time is greater than the sunset time, we can just subtract the time in which the sun had set at, and we know that's how far we are into our solar night prior to midnight. And if it's past midnight, we can find the amount of hours that we're past midnight based simply on whatever the actual time currently is. So rather than calculating the rotation over 180 degrees of movement, let's split it up into two 90-degree sections. If we just calculate each of the remaining degrees into this one quadrant of 90 degrees, and then add the amount of degrees that the sun has already rotated up until this point, then our sun should be, theoretically, at the exact position that we want. So, if it's after sunset, we would add 180 degrees, and if it's after midnight, we would add 270 degrees. Now, between these three algorithms, we should always find the perfect sun location, no matter what the time is, so that you can always enjoy those pretty sunsets and sunrises. And of course, the time in which your sun rises and sets at can be determined based on your location of the Earth and what date it is. And that can all be automated and programmed based on information given by the player, but I think that's a video for another day. Thanks so much for watching. We'll see you in the next one.